Ever wondered how engineers carve massive tunnels through mountains, under cities, and even beneath the ocean without the ground collapsing above? Today on Knowledge Hub, we're heading deep underground to explore the astonishing engineering of tunnel boring machines, the colossal mobile factories that quietly reshape the Earth. A TBM starts its journey inside a launch pit, where the machine is assembled piece by piece. Cutterhead, shield, backup decks, slurry pumps, transformers, and kilometer-long support trailers. Once launched, everything begins with the cutterhead, a rotating steel shield covered with tungsten carbide discs capable of crushing, shearing, and grinding through rock with pressures exceeding hundreds of tons per cutter. But the intelligence of the TBM lies behind that shield. Pressure sensors, earth condition monitors, torque meters, and load cells constantly measure the stability of the tunnel face. In soft soils or high groundwater zones, earth pressure balance machines inject foam and polymers to modify soil consistency, while slurry TBMs maintain face pressure using bentonite-rich fluid, circulated through high-pressure pipelines to a surface slurry treatment plant equipped with hydrocyclones, vibrating screens, and filter presses. Inside the TBM, giant gearboxes and multi-megawatt electric motors regulate cutterhead torque, and temperature sensors prevent overheating as friction builds. Acoustic monitoring systems detect microcracks in cutter discs long before they fail, while laser scanners map the freshly excavated face to show how the geology is changing. In unstable or unknown formations, the TBM drills probe holes far ahead to detect voids, faults, or pressurized water pockets. If risks are found, crews freeze the soil with liquid nitrogen or inject microfine grout to stabilize the ground. As the machine advances, the segment erector installs precast concrete lining rings, each consisting of multiple precisely engineered segments with steel reinforcement, waterproof gaskets, alignment dowels, and embedded sensors for long-term monitoring. Hydraulic jacks push the TBM forward by bracing against these rings, delivering thousands of tons of thrust. Behind the shield stretches a vast industrial train. Conveyor belts and muck cars remove excavated material. Rail bogies deliver new segments. Fire suppression systems protect workers. Cooling lines manage heat from motors, and massive ventilation ducts pump fresh air hundreds of meters below ground. Cross passages are excavated at integrals using smaller machines or controlled blasting to link parallel tunnels for emergency access. At the end of its journey, the TBM enters a reception chamber, also called a breakout pit, designed to safely stop and dismantle the machine. But depending on geology, water pressure, and tunnel layout, some machines cannot be retrieved, so engineers cut off critical components and leave the main shield sealed permanently behind the final lining. And here's where tunneling becomes even more fascinating. On long projects, engineers often dig from both directions using tunnel boring machines, aiming to meet with centimeter accuracy after kilometers of blind excavation. To achieve this, laser guidance, automated surveying, gyroscopes, and continuous GPS referencing of surface markers feed real-time data into steering joints that bend and articulate the entire TBM along the correct path. When the two machines finally meet, only the essential internal components, motors, hydraulics, electronics are dismantled and removed. The massive steel shield, sometimes 10 to 15 meters in diameter, is usually left buried, sealed behind concrete bulkheads, because dragging a multi-hundred-ton machine back through a finished tunnel would risk damage, settlement, and enormous cost. Many cities around the world have dozens of TBM shields permanently entombed underground, safely abandoned as hidden relics of their transportation networks. Above ground, sensitive structures like skyscrapers, roads, and pipelines are monitored with settlement gauges, tilt meters, fiber optic cables, and satellite-based InSAR imaging to detect even millimeter-level ground movement as the TBM passes beneath. The combination of geology, robotics, industrial automation, pressure physics, navigation science, and safety engineering transforms tunneling from a dangerous excavation into one of the most precise construction processes on Earth. And when the machine finally breaks through, it leaves behind a perfectly smooth tunnel ready for metros, highways, and high-speed rail, often with a TBM's forgotten steel body resting deep below as a silent monument to the engineering that built our world. If you're enjoying these deep dives into the engineering that shapes our world, make sure you subscribe to Knowledge Hub for more fascinating stories. And as always, stay curious.